Hello students, welcome back. Let us resume our discussion in section 2. We went through some elementary examples, some really elementary examples, and then a bit harder elementary examples. Now these examples here are no longer elementary. It is not entirely clear what to take as your substitution. Here, for example, if you take y as the entire denominator, okay, start from there, and then take the derivative. And you'll already see something is not going right. Take the derivative, and then we have a product rule. The derivative of the first function times the second function plus first function times the derivative of the second function. So we get log of x plus 1. And consequently, what are we getting? The x is 1 over 1 plus log of x dy. That's what you're getting, right? And this 1 plus log of x are getting really complicated. And then if you plug that back into this integral and try to do the simplification, good luck. And as a matter of fact, by this time, you must have already realized something is not going right. Remember, the purpose of this integral, purpose of all this technique is to make this integral simpler so that you can handle. And if you put this one in, okay, I started this, so let me just go one more step. Oops. Yeah, just one more step to do one more substitution. If I do that, I'm going to get something like, this entire thing is y, but then again, that times this. It's getting worse. So clearly this thing is not working out, and you'll have to find an alternative method. So this substitution does not work. How do you make it right? Well, let's go back to the step-by-step process here. And step 0 is the recognition. What do? It's the composite function, and y is the inside. That's what we used to do. But there is a second criterion. It's the derivative of the candidate present in the integral. We didn't have to consider this carefully in the elementary problems. This time we do. The derivative of this is 1 plus log of x, or log of x plus 1, but that's not present here. So something is not right. Now, if you just do y as log of x only, then the derivative is just 1 over x. And 1 over x is available here. Do you see that? Let me take a bit bigger font of this. Even bigger font, okay, alright. Do you see 1 over x? It is present. You see, the second criterion actually plays a role here. It played a role for other problems too, but this time it is really significant. So let's get this completed. So let's solve for dx. So flipping over, we get x dy. So that's blue. So this entire thing is integral of 1 over x times y times x dy. And this one red, and this one blue. Yeah, that's integral computation. Now that we saw that 1 over x there, we don't need to have a font this big, so let's go back to about this big. That's big enough. And then do you see cancellation? This x and that x going out. Consequently, we get the integral of 1 over y dy. So this integral is log of y plus c, and therefore this is log of x plus c. Remember, this y is log of x. Oops. Yeah, right. So we have log of x plus c. A little bit unusual substitution. We are simply taking log of x, not the entire denominator. And the reason is the second criterion. The derivative of log of x is 1 over x, and that's present here. How about the next example? If you take, say, another character, say u, as this entire thing, and try to work it out, good luck. It's not going to work. And of course, if you try to take the derivative of this, at that time you'll of course see it's too complicated. So how do you work it right? U is, let's go with the second criterion, the derivative of the candidate. The derivative of the candidate, derivative of something is cosine. We have some sines, oh right. That's the way to go. So u is sine of theta, so that we have sines here and there, see? And the derivative, that's cosine. So that's the second criterion. Okay, all right. du is cosine of theta d theta. Therefore, d theta is 1 over cosine of theta d theta, and no, that's du, that's blue, and that's going to go in there. Okay, so step 1, substitution. Step 2, derivative. Step 3, solve for d theta. Okay, all right. Let's go to step 4. Substitute everything back into the original integral. And this is going to be u squared, u to the 4th power. I don't know why I'm using the font color here. Let's bring those back. Okay, and then this one is 1 over cosine times du. Okay, that looks good. This cosine of theta and that cosine of theta canceling each other out, and you have integral of just polynomial function. This doesn't look too bad. U plus 1/3 u to the 3rd power plus 1/5 u to the 5th power plus constant. And then of course what I want is functions of theta, not functions of u. So I want sine of theta plus 1/3 sine cubed 1/5 sine to the 5th power. Looks like that completes the problem. You can check the answer. Take the derivative of this. Sine becomes cosine, so 1 times cosine. This one becomes sine squared times cosine. Indeed, sine squared times cosine. This one becomes sine to the 4th power times cosine. Indeed, sine to the 4th power to the cosine. Okay, one more problem, and this is the hardest of the bunch. Well, after this experience, you can now see you're taking sine of theta as your substitution. Is that straightforward to you? The reason is because of this cosine. The derivative is present. If you take 1 plus sine squared, entire denominator, and work out, well, be my guest. Try. If you take the derivative of that, you get 2 sine of theta times cosine of theta, and then some further algebra. It's not going to work out. And then derivative. Therefore, okay, we have that. We are ready. Let's take out a bit bigger font. Copy and paste. And this one here will be u squared. And this one here will become 1 over cosine of theta times du. After simplification, you're going to get this integral. 1 over 1 plus u squared du. What is this integral? It's a bit unusual, but it is well-known antiderivative computation. It is arctangent. Now, inverse trig functions are not very important in Calculus 1, so yes, this one is not that important in Calc 1, but in Calculus 2 it is important. Inverse sine, inverse cosine, inverse secant, inverse tangent, there are many. Among those, inverse tangent is the most important. Anyway, let's complete the problem. So it's inverse tangent of, what is u? U is sine of theta. That completes the problem. Inverse tangent of sine of theta plus e. Okay, we went through some problems associated to this criteria, the second criterion, the derivative of the candidate present in the integral. Among those, the first problem is the most important, especially in Calculus 2, and the second one is moderately important. Third one, a bit too much, especially inverse tangent and things like those.